Okay, so this lesson is on hyperbolas. On the application assignment, there is one question regarding hyperbolas that a lot of people tend to have struggles with. So I'm going to make sure to go over a similar example to that one. So let's just start with the definition of a hyperbola. So it is the set of all points for which the absolute value of the distance, or of the difference of the two distances from 2 points, the foci, or foci, each focus, they're constant. So basically, if you are on any point on the hyperbola, so I could be down here, this distance is constant. So as my point moves, the distance from the ordered pair and then the two foci, that's constant. It doesn't change. So that's what gives us the definition of a hyperbola. And the same thing if I'm on this side. Just the difference between that distance is the same. It's constant. It doesn't change. So when we're working with a hyperbola and we're writing equations for it, there are things like we need to know the vocabulary. So there are two distinct pieces, and I've seen people describe these as two sideways parabolas. They're not exactly parabolas. They look kind of like it, but these are called the branches of a hyperbola. So you've got two branches. You have a center, which is basically halfway between the two foci. It's also halfway between the two vertices. And then it's set up very similar to an ellipse in that the distance from the center to a vertex is A, and the distance from the center to a foci is C. So it's set up very similar to an ellipse. With those types of equations, it's almost like an inverted ellipse, where it's like instead of these things facing towards the center, they're facing outward. And then we have what is called the transverse axis, which is equal to 2 times A. And this D2, D1, that's that constant difference. So basically, this distance, oops, not from the vertex, from the foci, here, the difference between the distances there, the D1 minus D2, is equal to this distance right here. It doesn't look like it, but it is. So the book actually shows why that is true. Goes through, does some, goes through the algebra to demonstrate that. But basically, so that distance between the vertices we call the transverse axis. When you have an ellipse, we call it the major axis because an ellipse has 2 axes. A hyperbola just has 1 axis. So it's called the transverse axis. But in both types of equations, we use 2A to basically reference that. So this is directly from the textbook, just the equations of the hyperbola, and center H comma K, and it's very, very similar to an ellipse, where you basically have like an x minus h squared over a squared. The difference is that it's a subtraction versus a y minus k squared over b squared. So it's subtracting there, and an ellipse has a positive, has a plus. So very similar equations. So that one sign difference is the difference between an ellipse and a hyperbola. And then if you switch where the transverse axis is, instead of flipping the a squared and the b squared with an ellipse, you flip the y and the x part at the top of the fractions. But you're still kind of reversing places here. So we do have this equation that you can use to figure out the right here, the b squared that you need. Usually you can figure out a squared pretty easily. So to find b squared, you solve the c squared equals a squared plus b squared, and then that will be able to find you b squared, basically the unknown piece that we usually know for, or don't know, basically in our hyperbola that we have to find. What's different of a hyperbola versus like a parabola or ellipse is that there are actually asymptotes. And so the asymptotes are kind of, I mean, I don't know, if you make a basically like a rectangular square in between your vertices, then the asymptotes are the lines going through those corners. And so we've actually got formulas for the asymptotes. We don't really use these too often, so it's not something that you need to like memorize or anything like that. But if you do happen to need to find an asymptote, that's where those equations come from. So I've been sort of comparing the ellipse to a hyperbola because they are very, very similar here. So you can see that the differences here in their equations are just, you've got this plus here versus a minus in the hyperbola. So, but the equations are almost near identical. They've got the center equation, the vertices, the foci, those are all identical. The major axis versus transverse axis, it means the same thing. It's equal to 2a. There is a difference in how we solve for b squared. So if you're finding b squared with an ellipse, it's a squared minus c squared. With an hyperbola, it's the other way around. It's c squared minus a squared. So it's kind of, like I said, it's like an inverted ellipse in a way where it's like what's positive is now negative. And so it's the same thing here. So our positive sign became negative. And then also the signs between the a squared and the b squared flip. And then that's how it comes into this form. To demonstrate the similarity for the vertical version, so our vertical ellipse, we usually just flip the a squared and the b squared so that the a squared is under the major axis, which is vertical. But because this is addition, we can reverse that order and write it this way. And if you do that, you can see that even the equations for the vertical ellipse and hyperbola are very similar because the vertical hyperbola puts the y first before the subtraction. So there are a lot of similarities between the equations of an ellipse and a hyperbola, which makes it easy to get confused and accidentally write the wrong one. So just keep this in mind and make sure you're using your plus and your minuses in the right spot so that you're not accidentally, using the wrong equation, because I've seen that. I've seen people say they're going to do a hyperbola and then they give me an ellipse instead. So you want to be very careful. So we're going to just go through several examples of how you find the equation for a hyperbola given various information, and then I've got a couple word problems at the end to kind of demonstrate this. So our first problem here, we want to find the standard form of the hyperbola with vertices plus or minus 4, 0, and foci plus or minus 6, 0. So I always start with drawing a picture, and I recommend for all of the homework problems that you draw a picture so that you can make sure you have everything labeled properly. So not a very good grid, but I don't have to be exact. So we've got plus or minus 4 for the vertices. And the vertices are where our hyperbola actually goes through. So I can kind of draw our hyperbola there. And then the foci are at 6 and -6 here. So this is a typical horizontal hyperbola. So our equation is x minus h squared over a squared minus y minus k squared over b squared equals 1. So we need to find the center, we need to find a squared, and we need to find b squared. Now my picture is not to scale, so just FYI, my center does not actually look like where the center is because it's just a sketch here. But we'll start by finding the center. The center is the midpoint of the vertices or the foci, either one. So we have to go back to that midpoint formula to figure out the center. And so if we use the vertices, our center is going to be at -4 plus 4 divided by 2 And then the y values are 0, 0 plus 0 divided by 2. So our center is going to be at 0, 0, which you can kind of figure out just by looking at where those values are. But like I said, my picture is not to scale because my origin is not clearly in the center. But the key is that the center is the midpoint between the vertices and the foci. So we have found the center, so we know that H and K are both 0. Now we need to find A and B. So you can go back to our picture here where we have things labeled. A is the distance from the center to a vertice. And then C is the distance from a center to a foci. So in order to find B squared, we need to find both A and C. So first we'll find A. So this distance here is equal to A. And since our center is at 0, this is telling us that A is equal to 4. Because basically the distance from 0 to 4 or -4 is 4. And then this distance here is C. So since the center is at the origin, C is equal to 6. So we know H and K, we know A squared because we know A. Now we need to find B squared. And so this is where we're going to use that formula. B squared is equal to C squared minus A squared. So I have that written here because that's usually most of the time we're finding B squared. Very rarely are we finding something else. We usually know A and C, and then we need to find B. So all I need to do is plug in my numbers. So C squared, 6 squared, and A is 4, so that's 4 squared. So that's 36 minus 16, which gives us 20. So B squared is equal to 20. We don't need to actually take the square root of it because we need B squared in our formula. So I don't have to worry about taking the square root and dealing with that. I can just use the value of 20. So now we've got everything we need to actually put it into our equation. So our equation is x minus h, and h is 0, so we just get x squared there, over a squared, which is 16. Then we have y minus 0, which is just y squared, over b squared, which we solved is 20, and then equals 1. And so that's our equation for the hyperbola that has these particular characteristics where the vertices are at plus or minus 4 and the foci are at plus or minus 6. Are there any questions? Okay. So here's another one. Now our vertices are in different locations. The vertices are at 2, 3, and 2, -3. And then the foci are at 2, 6, and 2, -6. So again, I'm going to just sketch, if I can get the right color here, sketch my graph here. So we've got 2, 1, 2, 3. So we've got 1 point there, and then 2, -3. So these are vertices, so this is where the hyperbola goes through. So because they are vertically aligned, that means we have a vertical hyperbola. And so it's going to look something like this. And then we've got our foci 2, 6, and 2, -6. So the vertical hyperbola formula looks almost exactly the same as the regular formula. It's just the y and the x positions are reversed. So instead of x first, it's going to be y, and it's always y minus k over a squared minus x minus h squared over b squared equals 1. So the denominators for a hyperbola are still a squared and b squared in that order, but we flip-flop the numerators, basically, when we have a vertical hyperbola. And then you got to make sure you have that minus. So our center, once again, is halfway between the vertices, or halfway between the foci. Now, visually, you can see that this is, you can kind of figure out where it's going to be, that it's going to be at 2, 0, but we should go through the steps to actually use the midpoint formula, because not every situation is going to be that you can kind of figure it out that easily. So it's the midpoint of the vertices. So that's 2 plus 2 over 2. And you average the x values, and then you average the y values. So 2 plus 2 is 4. 4 divided by 2 is 2. And then 3 minus 3 is 0. 0 divided by 2 is 0. So our center is going to be at 2, 0. So h is 2, k is 0. Next step is to determine A and C. So A is this distance from the center here, 2, 0, to our one of the vertices, doesn't matter which one, I just happen to pick the 2, -3. So that distance between those is going to be 3. So we don't, A and C, we don't usually write them as negative. We're squaring them, so if it's negative, it's going to be positive anyway, but we usually take the absolute value. So because we're talking about distance, and distance is always positive. So even though what I drew, technically the difference there would be a -3, A is going to be 3 because we're going to just use its distance, it's positive. So A is 3, and then C is between the center and one of the foci. So it doesn't matter which one I look at, but I don't want to clutter up my picture, so I did the top part. That gives us that C is equal to 6, because the difference in the y values there is from 0 to 6, so that's a distance of 6 units. X values are the same, so we don't really need to worry about that. So once you have your A squared, or your A and your C, then we can find B squared with our formula, C squared minus A squared. So C is 6, so that's 6 squared. A is 3, so that's 3 squared. So we have 36 minus 9, which is 27. So once we have B squared is 27, if we go in this order, we've got everything that we need in order to write our equation. We just have to plug the numbers in. So we have y minus k, which is 0, and then you square that. So it's going to be y squared over a squared, which is 9, minus, and then we have x minus 2 squared over 27 equals 1. Any questions?
How come we don't square B?
B, we found B squared, it's already squared.
Okay.
Yeah, because the formula here is B squared minus C squared minus A squared. So since it's already squared, I don't have to square it again. I can just plug it directly into the formula.
Okay.
Any other questions?
Not yet.
Okay. All right, so third one here, we want to find the standard form of a hyperbola with vertices at -2, 1, and 2, 1, and passes through the point 5, 4. So in this case, we're not given a foci, so we have to do a bit more work. So I'm going to start by sketching what I have. So we've got -2, 1 and -2, or oops, -2, 1, and I misread my handwriting. Not my handwriting, I just didn't read my points correctly. And 2, 1. So since these are horizontally aligned, this is going to be a horizontal hyperbola. And these are the vertices, so the hyperbola is going through these points. And then we know that it goes through the point 5, 4, which would be like somewhere up here. So let's start with what we know. We know that this is going to be a regular horizontal hyperbola, so I can write down that equation. X minus h squared over a squared minus y minus k squared over b squared equals 1. So first step is to find the center, which is going to be the average, basically, or the midpoint between the vertices. So far, pretty much every step is going to be the same as what we've been doing. So we have our x values 2 and -2. And then our y values are 1, both of them. And so when you do this, you get 0, 1 as the location of our center. And knowing that the distance from the center to the vertices, that gives us A. So our vertices are at, that particular one is at 2, 1. And then our center is at 0, 1. So the distance between those two x values are 2. So we know that A is equal to 2. Now, in order to find b squared, we have to find c squared. And to find c, that's where you have to kind of figure out, well, what are the foci? And we don't have the foci here. All we have is a particular point on our hyperbola. We don't have the foci. So we need to do something else. So what we're going to do is plug in the information that we know so far, and we will actually we're going to plug in the information, the center A, and then that particular point 5, 4 in for x and y, and we're going to solve for b squared. So that way we don't have to find the foci at all because we don't have the information in order to find those. So when I plug this into our formula, so our x value we're going to use from this other point that it goes through. So 5 minus, and then h is 0, squared over, and then a squared is 4, minus y, we're going to use the y value at that point, which is 4, minus, and k is 1. And then we don't know b squared. And then this is equal to 1. So we have to solve this equation in order to determine what b squared is. So I need to add, I don't think I'm going to have enough room to do it entirely on this slide, so I need to make another blank slide for myself after this, so I have room. Okay, So we have 5 minus 0, so that's 5, 5 squared. So we have 25 over 4. 4 minus 1 is 3, 3 squared is 9, so that's 9 over b squared equals 1. And so we want to solve this for b squared. So when I have equations that involve fractions, I multiply both sides by the denominator in order to eliminate the fractions, or the common denominator. So that would be 4b squared. So I'm going to multiply both sides by 4b squared so that I can eliminate those fractions. So when you multiply 4b squared times the 25 over 4, the 4's cancel out and you end up with 25b squared. Then when we multiply the 4b squared times the 9 over b squared, the b squareds cancel and you have 4 times 9, which is 36. And then on the right, I'm going to get 4b squared. So now I want to solve this for b squared. And this is where I'm going to move on to another slide and recopy what I have. So I'm going to subtract the 25b squared from both sides so that I have those on the right. This gives me a negative 36 equals minus 21b squared. Then I will divide both sides by negative 21. So I want to leave it as a fraction. And we end up with 36 over 21 equals to b squared. But we can reduce this because 3 goes into 27 or 21 and 3 also goes into 36. So when I reduce that, I get 12 over 7 as my b squared. So now I know what b squared is, and that's what I needed to complete our formula. So we're going back and we're going to write our equation for the hyperbola. We're not going to plug in 5, 4 for x and y anymore. We're going to leave those as x and y, but we're going to plug everything else in. So we get x minus 0 squared over a squared. So a squared is 4. Minus, and then y minus 1 squared over b squared, which is 12 over 7, equal to 1. And then we don't leave our answer with a fraction inside a fraction, so that when you're dividing by 12 over 7, that's the same as multiplying by the reciprocal. So we're going to rewrite this as x squared over 4 minus 7 times y minus 1 squared over 12 equal to 1. So we're just, when you're multiplying by the reciprocal, now your denominator is going to be 12, and then 7 gets multiplied on the numerator. And that's how we write the equation for this particular hyperbola. Any questions?
None from me.
All right. So now the problem you've all been waiting for, the one that is similar to number 5 on the assignment. So in 10.4, the example 5 has very similar, like it shows you all the steps, and then there's a checkpoint exercise with different numbers. So I'm going to do the checkpoint exercise. And this is very similar to the assignment. The assignment is like you've got lightning instead of an explosion here, but the methods are very, very similar. So 2 microphones 1 mile apart record an explosion. Microphone A receives the sound 4 seconds before microphone B. Where did the explosion occur? And then we're going to assume sound travels at 1100 feet per second in order to complete this problem. So I like to start with my picture. Now, we don't know the actual locations of A and B, like if you were to put like X and Y coordinates on it. We don't have those locations, so we can put them wherever we want. If I wanted to put microphone A at the origin and then B to the left of that, I could. If I wanted to put B to the right of it, I could. Or I could put the center at the origin and then put A and B on either side of them. It doesn't matter where you put them as long as you were consistent with that throughout the entire problem, because it doesn't actually tell us where these locations are. So I tend to put my center at the origin because it just seems easier to me. And then I just go left to right and put A on the left and B on the right. But it does not matter. But the key is wherever you decide to put these, you need to have a picture so that way we know what you're starting with. Or you need to say, assume center is 0, 0, and assume A is here, B here, whatever. So I'm going to do it this way. And so I'm going to put the center at the origin. And I'm going to, just for good measure, assume the center is 0, 0. Just so we have that. So that will be part of our equation here. So what we know is that the two microphones are 1 mile apart. So that means, so if the microphones are at A and B, then the distance between A and B and the center are going to be half a mile each. So I'm going to just put 0.5 here. Now, they don't tell us whether the microphones are the vertices or the foci of the hyperbola. But in situations like this, they are always on the vertices. So I can draw my vertices through here. And so knowing this, I know that A is going to be 0.5 miles. So I need to write my units here. Now, because sound is traveling at feet per second, it would probably be good for us to convert this to feet. So we need to make sure that you show this conversion correctly. Use the unit conversion, the dimensional analysis to do this. I saw a lot of people doing this incorrectly on the last homework. People were not showing their work for unit conversions correctly. So when you do a unit conversion, you need to show it with multiplication. So 1 mile is 5,280 feet. So you're demonstrating that your miles, the units are canceling out here. And this gives us 2,640 feet. And you should always write your units there, especially when you have word problems. So we know A. And then the other issue here is that we don't actually know, like C, we don't have that information. We have some other information here that we need to figure out. So we've got the sound 4 seconds before microphone B. We haven't used this piece of information yet, and we have to figure out, well, what does that mean? Like, what do we do with that information, essentially? Actually, as I'm looking at this, I realize that I'm looking at this problem. Our locations of the microphones are not actually on the vertices. I misspoke there and misdrew. So we're actually at the foci because we're asking, okay, the sound is somewhere. If I have like a microphone here, it's going to catch anywhere in this direction. So wherever the microphone is located, you know, it could have a circle or something like that. We are actually not on the edge of the range. So we're not actually we're not the vertices, we are actually the foci, which means that it's not A that's half a mile, it's C that's half a mile, because C is the distance between our center and the foci. So I'm sorry about that. I had a little brain fart there when I was going through that and put us in the wrong spot. So think about these hyperbolas as basically the edge of your hearing range. And so it's like B can hear distances, something that occurs anywhere between, you know, this kind of thing in either direction. So we are not actually on our hyperbola. So with that correction, with us being actually one of the foci, or A and B are both being foci, these microphones, we have to go back to the 4 seconds. So microphone A receives the sound 4 seconds before microphone B. So the hyperbola that I've drawn is in yellow. That is our hearing range, like basically where they can hear the sound. So A will hear it somewhere on its yellow branch. B will hear it somewhere on its right branch. And all we know is that the differences, the distance between wherever the sound is equal to 4 seconds. Now we're going to make an assumption that we're going to take it at the closest part here, so that this is 4 seconds of time between these two locations. So we're going to just assume it to be on the horizontal because it will make our life easier. But that's not a distance, that's seconds. We need to convert 4 seconds to a distance to figure out actually what would be the distance that it traveled in that time. So we have to do a unit conversion. So 4 seconds, and then sound travels at 1100 feet per second. So we have to do unit conversion, where we use that to convert from seconds to feet. And so that gives us 4,400 feet. So now we know what that distance is, and that distance between the vertices that I've kind of drawn in there, the 4,400 feet, that is equal to 2A, because A is halfway from the center to one of the vertices. So that is equal to 2A. So we need to solve that to figure out what A is. So we have to divide that by 2. So that gives us that 2,200 feet is equal to A. So we have found C and we have found A, and we can use that information to find B, or B squared in our formula. So this is what I've drawn here is a horizontal hyperbola. We could have drawn this as a vertical because, again, we're just making lots of assumptions here because we're not given like actual ordered pairs here. So the equation that we use, the x minus h squared over a squared minus y minus k squared over b squared equals 1. So we assumed h and k are 0. So that just gives us x squared and y squared. And we have found a squared. So now we need to find b squared. And b squared is found with the formula c squared minus a squared. So we're going to have to plug in our values. So I'm going to move on to the next screen here. So C is 2,640. And then A is 2,200. So definitely calculator day here. I gotta make sure that I'm not missing any numbers. So we've got these large numbers that now I need to make sure I put in my calculator properly so I don't make any math errors. So this gives us that b squared is equal to 2,129,600. Now we can put this in our formula. So our formula, our center's at 0, so it's just x squared over a squared, 4840000, minus y squared over b squared, 29600 equals what? So now we have this equation that is telling us that we've got a hyperbola here, and we've got this equation for the hyperbola. And the question is saying, where did the explosion occur? Well, we've got an issue because we can't figure out where it occurred specifically. We don't have enough information basically, because we have the equation. We know it occurred somewhere on this hyperbola. So we know it's somewhere following this equation, but in order to figure out the exact order pair, we would either need to know an x value or a y value, because we've got one equation, two unknowns. So we can't actually find a specific location for where it occurred without a third point. If you had maybe a third microphone, then you could get a second equation from that microphone and one of the other microphones, and then you'd have two unknowns, two equations, and then you can solve and you can get an ordered pair. But we don't have enough information with just two microphones in order to figure out the exact location where it occurred. All we know is that it occurred on the hyperbola governed by this line. We can kind of figure out whether it's on the left or the right branch based off of who got the sound faster. So microphone A got the sound before microphone B. So based on my picture, it's got to be on the left branch, but we don't know the exact order pair because we don't have enough information. So what we can say is, based on our assumptions, so we had to make some assumptions with our picture and everything, the explosion occurred on the left branch of the hyperbola given by, and then we have our equation. There actually is an example in the textbook where they give you a third location, or they'll tell you in this section, in section 10.4, where they'll say, okay, we know that y is at this point. And then with that information, you can find where it occurred. But we don't have enough information what they've given us. So all we know is that it's somewhere on this hyperbola, and based off of our assumptions, it's going to be on the left branch. Are there any questions? Okay. So on that last question on the homework assignment, set it up very similar to this. I recommend assuming your center is at the origin because it makes your work easier. Show your work the way that I've showed here. You need to do some unit conversions, so make sure you're showing them properly. Keep the locations of where you're hearing things. Those are going to be the foci. The vertices are where it's actually, we're assuming that like we start getting the sound, you know, where they actually detect it. So if you follow this, you should be able to do problem 5 just fine. Now here's my last example. So this is another application of a hyperbola. So this actually is problem 50. I just took a screenshot basically of it. So we've got a base of a clock with the shape of a hyperbola, and they've been kind enough to label lots of ordered pairs there for us. So we want to write an equation of the cross section of the base. And that's essentially telling us we want to write an equation for that hyperbola for what we're seeing right now. Like if we took a cross section right now, this is essentially cross section. So we just, and the base, I wish I could kind of zoom in on the picture. I didn't want to take up the whole thing. This part, oops, I thought I was on a pen. This part is not part of the base. So we're just looking at the cross section of the lower part. That's the part that looks like a hyperbola. So we're writing an equation for that part. And then part B says each unit in the coordinate plane represents half a foot. Find the width of the base 4 inches from the bottom. So then once we get our equation, we need to use that equation to come up with our, you know, the actual distance there. So, oops. What I'm going to do is draw a bigger picture so that we don't have to zoom in here. So I'm going to just draw this kind of bigger. Well, terrible straight lines, but that's okay. So we've got the vertices based on our picture here are 1, 0, and -1, 0. And then we are given locations here. We don't need this many locations, but they're giving us 4 additional points there, 1 on each side of the branch, but we don't need to really know what those are, but I'll label these. And so this is our cross section of the base here. This is what we're looking at. It kind of looks like a cooling tower for those nuclear cooling towers. I think they usually have that shape. So we need to get the equation. We can see that the center here, we have to figure out the center. Our center is at the origin based off of our picture here. And it's because it's the halfway point between our 2 vertices. So we know our center is at the origin, and then A is the distance from the vertices. So we know that A here is equal to 1, since that's that distance from that center, 0, 0, to our vertices. And the book deliberately put the center at the origin just because it does make it easier for us. If we wanted to, we could change the scale, and you could say, okay, maybe this is where the origin is going to be, and then you have to like change all of your measurements to match up. But you need to, you basically, when you're given a word problem like this and you're trying to model it, if you're not told where the ordered pairs are, you have to make a decision where they are. Draw a picture so that way I can see what points you decided were where you decided to place your coordinate plane, so that way I can go off of where your work is. But they placed it right in the middle here, so that makes our center 0, 0. And so this is going to be very similar to the example I did where we weren't given one of the foci and we had to plug in an ordered pair in order to get our equation. So we're going to have to do that same sort of thing. Now this is a horizontal hyperbola, so we've got x minus h, which is 0 in this case. So squared over a squared, and a squared is 1, because a is 1. minus y squared over b squared equals 1. So that's where we have plugging in our center and a. And we need to pick one of these 4 locations to plug in for x and y. So it doesn't matter which one we plug in. We'll get the same sort of thing. So I'm going to just pick 2, 9 to plug into this equation. But it doesn't matter which of the 4 other locations that I plug in. But I'm going to choose that. So when we plug that in, so I'm plugging in 2 for x, so that's going to be 4 over 1 minus, and then it's 9, and it's y squared, so that's 9 squared, which is 81 over b squared equals 1. So I'm just going back to this equation, 2 squared over 1 minus 9 squared over b squared equals 1. So this is 4 minus 81 over b squared equals 1. So I can subtract 4 from both sides. We get negative 81 over b squared equals negative 3. Then I can multiply both sides by b squared so that I can get that out of the denominator. That gives us a negative 81 equals negative 3b squared. And then divide both sides by negative 3. And we get a positive 27 equals b squared. So part of A of the question says write an equation of the cross section of the base. So this is going to be our equation. It's going to be basically the hyperbola. That's going to be x squared over 1, so we don't even need to write that over 1, minus y squared over 27, because b squared is 27, equals 1. So that is part A, is to write that equation. Part B says each unit in the coordinate plane represents half a foot. Find the width of the base 4 inches from the bottom. So we're looking for basically what is this distance about 4 inches from the bottom. So we're going to have to do some unit conversions here because our graph, these are not in coordinate plane, values. So 4 inches, we got to do a unit conversion. So we've got 4 inches, and we need to convert it to feet because the coordinate plane represents half a foot. Or you could say that we can use 6 inches there, half a foot is 6 inches. So we can say there are 6 inches in 1 unit in our coordinate plane. So this is going to be 4 over 6, which is just 2/3 units. So we're wondering, we want to find the width when we are 2/3 above the base as far as y. So we're 2/3 above -9. So we are basically saying, okay, when is y equal to -9 plus 2/3, or -8 1/3? Based off of our picture here, because our bottom here is at -9, and so 4 inches from the bottom, we converted that, that's 2/3 units based off of our picture. So we're looking at where y is equal to -8 1/3. So our width is based off of x, but it's going to be 2 times x because x is just giving us the distance from our center point to the out. So we're going to have to plug this number into our equation for y, solve for x, and then multiply that answer by 2 so we can get the total width. Oops. So so we've got y equal to -8 1/3, which is, if I do the conversion to, that's -25 thirds. So that's what we're going to be plugging into y. And so we're going to get some really nasty stuff with some fractions here as we try to solve this. So I have x squared minus -25 thirds squared over 27 equals 1. Now, you might be someone that likes to get rid of fractions, so maybe we can multiply both sides by 27 so that we don't have that extra fraction on top of a fraction thing. So that would give us 27x squared minus, and then I'm going to go ahead and square the -25 over 3. So 25 squared is 225. 3 squared is 9. And so we end up with, oops, 25 squared is not, that's 15 squared. 625. Good thing I double checked that on my calculator. I was like, that doesn't sound right. 25 squared is 625. 3 squared is 9. So now I've got 27x squared minus 625 over 9 equals 27. And if you want to avoid fractions, we can multiply both sides by 9 to get rid of that fraction. So 9 times 27, we get 243x squared minus 625 equals 243. So I'm going to add 625 to both sides. $243x squared equals 868. Now I have a feeling that this is not going to come out nicely. You divide both sides by 243. Yeah, this is going to give us a fraction. I'm going to just round it to well, I don't want to round too much. So 868 over 243. So I'm going to just double check that I haven't done any math errors here because it is such a weird number. Other than my squaring of 25, which I corrected. I don't see anything here. So got the right numbers. But we're not done because we just found x squared and we need to find out what x is, and then we need to multiply that by 2 because we're looking for twice the width. So I need to first take the square root of this number in order to find x. So x is equal to the square root of our 868 over 243. And this, I'm going to just kind of, this is just going to get really gross. So I'm going to just round this because at some point we can't just, these fractions are getting kind of out of control. So my calculator is giving me 1.8899779. And now these are in units, because this is everything we're working with is terms of units from our picture here. So we're not in feet or anything, we're in units. Now the total width is twice that. So I need to multiply that by 2. I'm going to just do that on my calculator. 3.779955799. So that's our total width in units. Now notice that I didn't just multiply by 2 and write 1.88 whatever equals 3.79. You have to do it as a new line because we're multiplying x by 2. We're not just multiplying that number. I've seen a lot of people write x equals 1.9 equals 3.8. Those are 1.9 is not equal to 3.8. If you're going to multiply something by 2 like this, you either need to do it on both sides of the equation or you need to write a new line so that everything's equal. So we've got our total width is 3.8 roughly. And we need to convert this back to feet or inches so that we can, actually figure out, well, how wide is it? So we have to do another unit conversion. So let's do 78 units. And they told us that our 1 unit is half a foot. So I could say 1 unit is 0.5 feet. I want to just leave it in feet instead of doing the inches like I did before. So that's 3.78 times 2.5. I mean, that's basically going to undo our multiplying by x, or multiplying by 2. And so the width is about 1.89 feet rounded. And that is the second answer. That is the answer to part B. So if I go back to the original, each unit in the coordinate plane represents half a foot. Find the width of the base 4 inches from the bottom. So 4 inches from the bottom, our width is 1.89 feet. So many steps to this. Have to do several unit conversions. Do you guys have any questions?
It looks pretty intense.
Yeah, this what we did just here is actually there is a problem on the assignment where you do this with a parabola because you've got an arch. So when you do that problem, this is how I want you to show your work when you find your total width and stuff. So there's some similarities. This will help you on some of the other problems as well. So that was my last example. And we are a little bit beyond an hour, but I appreciate that you guys showed up, even with my mix-up on when I sent my reminder. That was on me. I scheduled it at the wrong time. So, are there any overall questions on this?